All right, hey folks, welcome to another installation of the HPC workshop series. Um, this week's topic will be tackling error handling and debugging. So we're going to try and take a sort of broad approach, going to give you some tips about this. As always, if there are any questions along the way, feel free to ask. Let's jump into it. So the scope of this workshop, just to kind of set the expectation of what we are going to cover and what we're not going to cover. So what we will cover are some coding best practices, some practices related to using the HPC, some general principles for debugging, how to get the most out of using AI tools to assist in your debugging process, additional categories and contexts for errors, how to get the most out of error messages, and more, right? So just to sort of set the expectation here, what we're not going to cover is every possible error message that you could see during your work. We're not going to be covering the specific bug that you got last week. So if you have specific questions, we're happy to take them. We do offer one-on-one consultations, but that's not the purpose of this presentation. And we're not going to cover your particular specialized software or software stack. So in this workshop, we're going to kind of take a very general lens at approaching errors and debugging, whereas if you need specific help, we do offer individual consultations. You can contact the HPC consult team through ServiceNow, and I guess I didn't put one on this particular slide, but there are links to that ServiceNow page later in the presentation. So if you have the Google Slides, you should be able to find that link. So this workshop will assume that you have a little bit of coding experience and that you have at least a little bit of HPC experience. So tackling error handling and debugging is not going to make a whole lot of sense to somebody who has zero coding experience. And some of the things we're going to talk about relating to using the HPC are not going to make a whole lot of sense if you have never used the HPC before. So if you are new to either of these things, welcome. We're glad you're here, but this might not be the best place to start. I recommend starting at the beginning of our workshop series and trying to get a little bit of experience with using the HPC and maybe encountering some errors before we actually, before you go ahead and try to take this workshop. So yeah, that's what I just said. That being said, this workshop's not going to be too advanced. We're going to kind of try to cover things from a general perspective. We're not going to get into the nitty-gritty of a whole lot here. So it should be accessible and helpful to both novice and intermediate HPC users. If you are a vet, if you have been using HPC since the 1980s, this might not be nearly advanced enough for you, but our target here is novice intermediate HPC users who are having trouble, diagnosing whatever errors they might be running into here. So if that sounds like you, welcome. We're going to jump into it now. So some terminology to start off with, just to sort of lay the groundwork, that making sure that when we use these terms, we're all on the same page. So an error is anything that causes a program to fail to execute as intended. Results of errors can include undesired behavior, unexpected output, freezes, crashes, anything up to system failure. So it could be just, when you run your program, you get a weird value out of it, and it just doesn't behave the way that you expected it to. That could be considered an error. Another type of error could be one that causes your computer to crash and need to restart. So there's a whole array of different results that you can get from your error. Hopefully, we're not looking at too many system failure errors here. We're hopefully going to be tackling errors that cause things more, even if your job fails for something like an out-of-memory error, that's something that we'll be able to talk about here. Bug, pretty much used interchangeably with error, but in my mind, I think of bugs as being a smaller error somewhere in the code, something that's usually a minor fix. Even if it can cause major issues, it can be, as simple as adding a closed parenthesis or fixing a typo. So in my mind, a bug is like a little smaller, even if its effect can be large. And an error can be pretty much anything. And we'll talk about the different types of errors as we go along. So an exception is also related to these two things. So it could be unusual conditions or behavior that needs special handling during the execution of code. And that is pretty general. Oftentimes, programming languages have exception handling built into them. So if you use Python, you might be familiar with try and I think it's try except or try catch. I can't remember the terminology exactly, but that's the idea is that you put something that you want to do, the unusual condition you would put in the try block, and then you would catch the exception by printing out a statement and having the program exit in a way that is safe and preserves your data, for example, rather than, you know, if the program were to terminate and you would lose all of your work, right? So exception handling can be performed at the code level as well. So some more terminology here, just continuing along. Dependency is some software or package that is required for a different piece of software to run. So if I want to use, say, matplotlib in Python, this piece of software has a number of different dependencies that are required for me to install those as well in order for it to run. And oftentimes package managers, as we'll talk about later, will handle this for you, but it's important to be aware of this piece of terminology, and it's important to be aware that when constructing in a software environment that has multiple dependencies, that can be a source of errors. So level, here I'm talking about programming level. So proximity to hardware, basically that low level programming involves more direct communication with hardware components, whereas high level program is a bit more abstract and encapsulates, hides the lower level functionality. So just to demonstrate this, a lower level programming language would be something like assembly. C would be also considered generally a low level program, although it does have some abstraction built into it. And then Python would be a much higher level programming language because you're almost never directly interacting with hardware components. You're never really directly managing things like memory, right? So just to continue on that, the low-level programming is less abstract because the objects of reference are closer representations of physical components, whereas in high-level programming, it's more abstract because the objects of reference are software objects, such as an array or a string. So if you're programming and the only things that you're operating on are arrays and strings and objects like this, then those are abstractions. Whereas in C, if you're looking at memory registers and bit shifting, things like this, that is less abstract. It's more directly related to what's going on inside of the physical components. So that's level. And then log, the last piece of terminology here, it's just a file that keeps a record of program output, and we will be talking about those a little bit. So with these out of the way, let's talk about some best practices. So the best way to get rid of bugs and errors is to make sure they don't happen in the first place. So we want to talk about a few strategies in a few different contexts that can help prevent errors. Okay. So, second. There we go. All right. So when we're writing our code, so this is if we are directly writing our scripts, managing, writing the piece of codes that are actually going to run on the HPC. So first is read the documentation. You might see this repeated in a few places, and I'm zero indexing this because this should always be implicitly the first thing that you do no matter what. Make sure you understand the functionality of different components of your code before using them. So if I'm writing a program that uses, for example, pandas, Python library for data handling, then I want to go at least, I might not have to read the entire documentation before using it, but I at least want to find out what the basic functionality is of different components so that I know how to use them and that I'm referencing that documentation as I'm writing. First tip here, first real tip is write modular code. And what this means is to split your code up into functions, modules, packages, etc., based on their functionality. If I have a lot of things that are happening in my script, I don't want to just write one big long script that doesn't differentiate between any of the functions unless you look super carefully. You want to make those functions very obvious. And that way, when errors do happen, they're a lot easier to find and a lot easier to fix. So large, simple purpose scripts are often more error prone than a system of components that can be used for a variety of tasks. And the good thing about writing these systems of components is that they can be repurposed for other tasks as well. I don't have to rewrite that particular function because now it already exists, right? So it makes your code more efficient as well. Include comments. It's easy to overlook. It's easy to say, why should I waste my time writing comments? But it will help you remember how parts of your code worked after you haven't looked at it for some time. So obviously, in these projects that we're working on, they can be large, complex. I might be working on one piece of code today, and I might be working on a different piece of code tomorrow. So it's easy to forget. We're only human. So include those comments, even if they're just for yourself. They don't have to be super pretty, but just something there to remind you what's going on if you lose context. And the last one here on this slide is test carefully and scale up. So don't attempt to run production-sized jobs before you have tested your code on a smaller scale. So don't try to run a 1,000 CPU job on the HPC until you have tested your code to make sure that you're not bringing down a bunch of nodes on the HPC, right? You want to make sure that your code is functional and does what you want it to, and also that it's not, wasting your compute time allocation. So testing carefully is always important. So there's a few more here. So just as you're creating your code, try to use descriptive names and stick to a convention. This will make it easier to avoid syntax errors and avoid ambiguity in the function of different variables or methods or whatever it is that are in your code. So descriptive names and trying to use some sort of convention. I know it might seem silly or trivial to use a convention, but it takes a lot of the work out of coming up with names and recognizing them and makes it more immediately obvious as you're looking at your code what's going on. So that's always helpful. So implement explicit error handling. So the syntax is different for each language, but most have some type of try-catch system, as we talked about with exceptions, that are built into the language so that you can anticipate and handle errors before they break your code. Or if something does come up, you can put it in that try-catch block, at least temporarily, while you figure out the best way to handle this particular context. And then once you figure that out, you can remove the try-catch block once it's been implemented in a way that is robust to whatever error that you were getting before. So those are our best practices for writing code. Now we'll talk about some best practices for using the HPC. And in particular, these best practices are not just general HPC best practices, but best practices regarding the use of your HPC in order to avoid getting errors and bugs and stuff. So particular to our topic here. So these refer to techniques you can implement while using HPC in order to avoid errors later. So first, once again, I'll say this is probably always going to be the first one here. Read our documentation and or ask for clarification. Our docs provide a lot of useful information, and if you can't find what you're looking for in our docs, HPC can help you out. And then, if it turns out to be something that needs to be in the documentation, we'll add it. So you asking us for help also helps us create better tools. So feel free, don't hesitate to ask us for help because we can always improve our documentation as well. So keep your files organized and clearly named. That's pretty self-explanatory. Always include log and error files in your batch scripts. So here's the syntax in the directives section of your batch script that you would need to include in order to have your job produce error files and output files. So the difference between an error file and an output file is that the output file contains the standard system out. So anything that would be in a print statement would show up in this file. And then the error file would be anything that shows up as a result of an error. So if your job fails, it's certainly good to look at both, but the error file might be the one that actually contains the error message that you're looking for. And if you put print statements in your program to help debug, those would show up in the output file. So it's important to know where to look for different types of information, but including both of these is always highly recommended. I do it for basically every single one of my jobs other than the most trivial ones. So we also have a workshop on managing and optimizing jobs. You can find that in our HPC workshop calendar or on the page for previous workshop materials. So I definitely recommend checking that out just because there's a lot of good tips and tricks in there. Obviously, this presentation is more related to bugs directly, but managing and optimizing jobs is also a great way to learn how to keep track of things if you haven't seen that one already. All right, so with those best practices out of the way, let's start to talk about errors. And the first one I want to talk about is syntax errors, because these are very common and they can have a variety of different effects depending on exactly what they are. But typically, they're the easiest to fix. If you're using an editor, a modern editor like VS Code or Sublime Text, or if you're using tools like the Python debugger, anything like this, oftentimes they can just find the syntax error for you. So it's usually pretty easy to find. So let's talk about these. So they're a common type of bug, usually associated with user error in syntax. You know, you're typing something and you got it wrong. So you made a typo, whether it was a misunderstanding of the way that syntax is supposed to work, or whether it was just an accident slip of the finger. Sometimes it can be due to different versions of code being run in the wrong context. Say if I have a script that I wrote in a newer version of the code on my laptop, and then it goes over to the HPC where it's running on an older version of the code, maybe they changed something between those versions that cause a syntax error, you know. This is not always common, but it does happen. So it's important to be aware of different versions having different syntax. So this type of error, as I mentioned, can, not always, but can be easy to identify and fix, especially with modern editors and IDEs. So IDE, if you don't know, interactive development environment. Sometimes, you know, the line between editor and IDE is kind of blurred at this point. So VS Code would probably be considered an IDE because of all of its functionality. So there's all these tools that can effectively do this for you, or at the very least provide some kind of assistance if it can't tell you exactly what the error is. And oftentimes the error messages may tell you exactly where the typo occurred. So generally best to rule out this type of error before checking on other error types. This is also the most common. So this will probably be something that, especially if you already have experience coding, that you are used to checking for and used to fixing. So with that out of the way, we're going to try to get into some more interesting and more tricky error types. So syntax errors, common, not always the easiest to fix, but generally not the most insidious type of error. So debugging. Let's talk about what debugging is. So debugging is the art and science of finding errors in your code. And I use both of those words for an intentional reason. So science is because it helps to be systematic in your approach to debugging. And it's also an art because it can be very nonlinear and very associative. You build intuition by debugging. It's something that comes with experience. So even if you are being very systematic, if you're not familiar with a variety of different error messages or terms or contexts or a million other things, it can be a bit challenging at first. So it's an art because it's something that you learn through practice and skill and by doing. So the nature of your debugging process can be very different depending on the language you are writing in. And this is why we introduced the idea of levels earlier. So a low-level language might have different types of errors that are common rather than, or as opposed to a higher level language like Python. So the types of errors that you're going to get when trying to run a Python script are going to be pretty different than the types of errors you're going to get when trying to compile and run a program in C. So that's important to be aware of as well. So finding bugs, how do we find them? That's really the question here. So of course, sometimes the error message will tell you exactly which line in the code the error occurred at. You should go look for it. So should go without saying, but it does need to be said, read the error messages. They do contain a lot of good information, and it is not uncommon for folks to shoot us a message saying, hey, I got this error, and then the answer is right there in the error message. So please go ahead and read those error messages. I know that sometimes it can be difficult to decipher, so it's no problem. We will certainly help you read through that and identify the information that's relevant, but you should at least try to read it. If it's not easy to identify where exactly the error in your code occurred, print statements are definitely your friend. So placing print statements in strategic locations within your program can help you locate errors a lot easier than simply guessing where they occurred. So this can look like printing out numbers in order, like 1, 2, 3, 4, 5. And then you can look at the output of your program. And if you see that it terminates after the program prints out number 4, but it didn't get to number 5, then you know, okay, that error is somewhere in between print 4 and print 5, right? And that'll narrow it down to that location in your code. So that's a good way of trying to narrow things down, and then you can get a little bit more granular with that, or printing out things that are more detailed as well. So you might want to print out the contents of a variable or an array or something like that that is occurring at a particular time. Sometimes it may be necessary to include print statements in for loops so that you can see the value as it's changing, and then you can identify what's going on. Including more detailed information is especially important if the error seems to be about formatting. So if you don't know how it's getting formatted, you should look at that in order to determine whether it's the correct value or not. So print statements are your friend. More things for debugging. The overall process does tend to be highly iterative, which means make a little change, run the program again, make a little change, run the program again. And it's important to have patience. It's important to realize that this is just how it goes. And even if you don't find it on your first try, it's a scavenger hunt, right? So be patient and be persistent, and you will find it. So the general process might look like this. So first step, you get an error, then you adjust your code, then you run your code, and then if you receive an error, you adjust your code again. If not, then you celebrate and move on to your next task. So the adjustments that you make are going to be highly context dependent. So I can't tell you exactly what adjustment you need to make for the bug that you're getting right now, but I can tell you guiding principles that might help you determine the best way to adjust your code to avoid that error. Of course, the devil is in the details. So again, it's a lot of exposure, it's a lot of practice, it's a lot of building intuition for these things. Okay. So I want to talk about the systematic mindset for finding bugs. So it's important to adopt the right approach when you are undergoing this task. So confusing error messages can be frustrating, right? So rather than just randomly guessing or just shutting your laptop and giving up, we can take a systematic approach to work through the errors. So first is just keep track of everything. You can copy your error messages to a notes document. I do this pretty frequently to keep track. That way, because if you're working in a terminal, the terminal does have limited output generally, so you can only scroll back a certain number of lines before the output disappears. So if you're doing this a lot, especially if the error messages you're getting are very long, it's not a bad idea to copy them over to a notes document or just have a program dump its output into a text file. So, and then that way you just have it sitting around and you can keep it around until you don't need it anymore. Write down the changes that you made and if they altered the error message in any way. So this will help you keep track of what types of changes are helpful for different types of bugs and which types of changes are not helpful for different types of bugs. And then the change in the error message. So sometimes you make a change and that causes a new problem. So you have to go undo that and then figure out what's going on. So it's very important to keep track of what's going on. Trying to just remember everything that you did is not necessarily the best unless you have perfect memory, which I'm very jealous of you if that's the case. So if you're mortal like the rest of us, I definitely recommend writing down your changes, whether that's physically writing it or just keeping a note on your computer, whatever works for you. So identifying keywords and phrases in error messages is also important. This is something that does come with practice, but does get easier as you continue doing it. Follow the trace back to the root of the problem. So oftentimes, if you're working with a complex program that has lots of dependencies and is linked to other pieces of software, the error message can go through multiple different files in the source directory for that program. So it's important to follow the traceback, find out where along the way this error actually did occur. And sometimes you can go find that piece of code in the source, and maybe you have to edit the source files. That does happen every once in a while as well. Sometimes you need to add an extra include statement in the header of a C file, or sometimes you need to remove it or change it, something like this. So identifying the keywords and phrases and following the traceback is good. So the thing with identifying these words and phrases is they will tell you whether the program arose from your code, whether it arose from some dependency that you're using, or maybe the environment or something else. This might sound a little obvious, right? But search for the things that seem the most important. Rather than Googling the entire error message, pull out the part that seems the most relevant. And it's a little bit difficult to say in general what makes something the most important or what makes something the most relevant to your error message, but do your best and you'll learn with practice. See if you can find a thread on Stack Exchange or somewhere similar where real people have discussed the issue. The closer it is to your question, the better, but sometimes you can learn something from this thread or from whatever it is that you're looking at, even if the error isn't exactly the same. You can maybe take the approach that they used and apply it to your situation. So these are a few things relevant to the systematic mindset. So keeping track of everything, writing down the notes, identifying the keywords and phrases, following the trace back of the problem, and finding the things that seem the most important. So also I want to talk about growth mindset with debugging. So a master bug hunter is not made overnight. It can take a long time to develop the skills that you need. And I definitely remember, I mean, I still know master bug hunter, but I remember first learning these skills. It can be pretty frustrating. So as long as you're learning something, I think you should be happy with your approach, or at least try to be, right? You know, it can still be frustrating. But that's why taking a systematic approach is good, because then you can learn things much quicker rather than guessing and not, if you fixed a bug just purely by chance, you're not going to learn anything because you didn't know why the fix worked, right? So try to be aware of why a particular fix worked. And sometimes it's not clear. Sometimes that's just the way things are. But do your best. Try to learn general ideas and skills and taking a systematic approach. These are very important attitudes to have. Details will oftentimes come with experience and careful note taking. So definitely be focused on the process, be focused on just learning what you can as you go along. And of course, ask for help when you need it, whether that's asking your fellow lab mates who are familiar with the software that you're using, whether that's asking your PI, whether that's asking the internet, whether that's asking HPC Consult. There's a lot of resources around. You don't have to do it alone. So try to ask for help when you need it. I know sometimes in certain situations, it can feel like there's nobody around that knows what's going on that can help you, but whether it's online or from some resource on campus, I'm sure you can find somebody that can at least point you in the right direction. So AI tools, I want to talk about that now because they are another good resource, especially as I was just talking about, if you feel like there's nobody else around that you can talk to about the problem, nobody else that's going to understand what's going on, sometimes asking an AI tool like ChatGPT can be very helpful. But it's important to note that while they can be helpful, they can also be misleading. So I want to give you some tips for getting the most out of these AI tools and trying to avoid them leading you astray. So generally, the sort of picture that I have in my mind here is that you're sitting down with ChatGPT and asking it questions. I haven't actually used GitHub Copilot, so I don't have many recommendations for that in particular, but I assume that these chatbots more or less work similarly. So if you have a problem, if you have something that you are trying to figure out, try to start by providing as much context and information as possible. So pretend you're explaining your situation to somebody that has no idea what you're doing. When I'm putting a question into ChatGPT, I really like to imagine that I'm telling this to a person and that I'm trying to provide them with as many details as I can. So sometimes the initial question that I would put in there would be pretty long. It doesn't have to just be like, how do I fix this, right? You can say, I'm doing this with this backend with these codes, trying to do this on an HPC system. And when I do this, this is the type of error message I get. And, copy and paste that whole error message in there. So it is possible for the chatbots to make inferences from context, but it's best to make sure that they have as little to guess about as possible. So generally, start by providing context and information. And when it does provide a response, take it as a suggestion rather than a definitive answer. So it's not going to actually know exactly what's going on. It has no way of knowing exactly the situation that you're in other than what you tell it. So just like the first thing that you try while you're debugging is not going to work, the first response that you get from a chatbot might not work. So remember your growth mindset. Even if the suggestion didn't work, maybe you learned something new from the chatbot, right? So I have learned a decent amount from them just by having them tell me about different aspects of codes that I wasn't aware of, even if it wasn't the exact fix that I needed at the moment. So remember, as long as you're learning something, you're doing right. And then keep the conversation going. So it's an iterative process, right? So tell the chatbot what you did. You put your problem in, you get a response, you go do something with your code, and then maybe you get another error message, or maybe you get a different error message, whatever it might be. Tell the chatbot what you did, what result it gave you, and then sometimes it can come up with new suggestions and be iterative. So just like the bug fixing process on your own is iterative, it might be iterative while using the AI tool as well. And do remember that the chatbot has some memory, not infinite, but some memory, and it understands the context of the conversation. So you can build off of new information, and it does sort of remember the conversation in a way. It's not perfect, and sometimes it'll lead you astray, but it does remember the conversation. Continuing with AI tools, recommendations here. So ask general questions. Sometimes even if you're looking for a very specific answer, it might help you to learn what the function of something that you don't know how it works is. So, I might ask it, what is the purpose of the glibc package? And general questions about the functionality of the system or about the functionality of your code can help you learn to be a better programmer, especially if this is, oftentimes these sort of like system ideas can be very nebulous or unclear to us as users. So I definitely recommend asking general questions about things as well as you're going through it. If you're curious about anything, if you're like, man, I really wish I learned this in a class, just go ahead and ask the tool. As I'm going to mention here in the next one, supplement this with concrete research. Always take what it tells you with a healthy dose of skepticism. Don't fully trust anything it says until you either one, test it for yourself, or two, confirm from a reputable source written by real human beings, again, from a reputable location, whether it's a textbook or something else, right? Documentation, whatever it is. So ask it these general questions, but then make sure not to take that with a grain of salt. Make sure to be skeptical. Make sure to do your own research to back up what it says. So this is very important. Seriously, I'm telling you ways of using the AI tools now, but it is so, so, so important to not take their word for anything at all. I like to picture the AI tool as somebody who has a lot of information but is not particularly smart. So it might not know how to put the information together. It might not know how to, um, you know, give you the best answer that you need. It might, it is possible for them to hallucinate, to make things up. So important to always supplement anything that you do with the AI with either direct testing or concrete research. And then also it can be useful to ask it for resources. So rather than taking its word for it, ask it to point you to somewhere reputable that you can go read that resource instead. So if you're having trouble finding information that's useful to your particular problem, it might not be a bad idea to go to ChatGPT and say, hey, can you point me to a resource on this thing that I'm trying to figure out? And sometimes it can hallucinate, but sometimes it will suggest something very helpful. So again, don't trust anything until you've verified it for yourself. But asking it for external resources is definitely an approach that I recommend, because if it does give you something real that you can go to on the internet, then you can see where that's coming from. You can see whether it's a reputable source, whether or not to trust it. And if it does have good information, then you have now a gold mine of information relevant to the problem that you were working on that you might not have had before. Again, always check for yourself. So the AI tools are great at giving suggestions, not results, right? So make sure to keep that in mind. Okay, so just a reminder, the chatbot is typically, these things are language models, LLMs. They're not knowledge models. They're not actual real representations of knowledge. They're representations of language. That might be a fine line depending on who you talk to, but for me, I like to keep that distinction in mind because it helps me interact with them in a way that's a little bit more helpful. So take what you can from it, but don't fully rely on any AI tool. Make sure your answer comes from either human written resources, hands-on testing, or both. AIs probably don't know specific detail about software functionality or compatibility. Try to use it to provide context and answers guiding and answer guiding questions rather than fill in the specific details. It's a compass that can point you in the right direction, but it can't tell you exactly where the buried treasure is. And of course, we have here an AI-generated pirate cat for this. Okay, so that's it on AI tools, I believe. So if there's any questions, feel free to ask away. Otherwise, we will continue. So common errors on HPC. So now we're going to talk about actual errors that you might run into while you're using the HPC. So Slurm configuration errors, environment errors, out-of-memory errors, file time errors, etc. And as we talked about before with syntax errors, it's always possible to have a syntax error in any of these contexts. For brevity, we're going to just assume that these can be detected and avoided. Instead, we're going to focus on errors related to the configuration of these systems. Okay, so starting with Slurm configuration errors. So effectively what this means is that something about the combination of parameters that you provided to Slurm resulted in an error. So possible outcomes for this would be that the scheduler doesn't accept your job and that it's not entered into the queue. You would usually get an error message relating, telling you this pretty much right away. Or the scheduler does accept your job, but it will never start. Lastly, the scheduler accepts your job and it does start, but it fails immediately. Typically, if the job does start and runs for some period of time and then crashes later, the problem is probably not due to Slurm configuration, but something else. So let's go through each of these cases. So category 1 example here would be I'm trying to start an interactive session on Elgato and I misspelled my group name. Or, I could potentially have provided it with a valid group that I'm not a member of, and I would get the same error here. So this would technically be a syntax error, but I'm just using this to illustrate the idea here that the job doesn't start because of something about the configuration. So the error message tells me that my error is related to the account or partition. So I've highlighted this bottom line here. It says job submit / allocate failed, invalid account or account/partition combination specified. So this is just telling me here, even if I don't understand exactly what that means, I can see the words account, I can see the word partition. So I might guess that in my Slurm configuration, I need to go look at either the account or the partition or the combination of the two that might not be valid. So if this were a batch job, I would need to look at the appropriate directives, batch directives. Okay. For category 2, where the scheduler accepts the job, but it will never start, it may appear as though there is no error at first, and you might not realize anything is wrong because the scheduler has accepted the job. It says job number, whatever, accepted. So use SQ to check on your jobs. So for example, if I use SQ, this is just an example that I wrote down. It's not a real job. But if you look at this, you do see here that the job is in the queue. Its state is pending. And if I don't look too carefully at it, it might just look normal to me, right? But if I look at the reason code, which is the thing on the very most right-hand column, that does tell us something. So do you have any interpretations as to what this reason code means and why that job might not start? And feel free to share if you do have any interpretations. So this reason code here says dependency never satisfied. What could that mean? What does it mean that if a dependency is not satisfied? In the case of Slurm, dependency here means a job dependency, not necessarily a software dependency. So I could have another job. So in the chat, we have an answer. It says no resources. Well, in this case, so if the reason for the job not starting were related to the resources, it would certainly say something. I would think that word resource would show up in the reason code. So Slurm, luckily enough, does have documentation on what the reason codes are. So if you wanted to, you could go to this official Slurm documentation website. You could find the page on reason codes, and you could then search for the one that is listed on your job. And then it would tell you what that means. So in this case, I think maybe my screen will continue sharing. So why don't we just go ahead and do that as a demonstration? We don't have a ton of time left, but I don't think this will take too long. So Slurm, let's go here. And so Slurm users, that's where I'm going to want to look. Here are all of the different documentation pages. So let's go to job reason codes. And then if I go to job reason codes, here are the common ones. But then if I go down, I see that there's a million of them down there. So if I look for dependency, so I see that one at the top. So here below that, dependency never satisfied. So that's my job reason code that it said on the slide. And it says this job has a dependency on another one, on another job that will not be satisfied, that will never be satisfied. So that means that there's another job that this job is, that job needs to complete and finish before this job can start. And what that means is that with this job, it probably failed. And, oh, yeah, I had that linked there. Cool. So what the job dependency thing means is that job A maybe failed in its execution, job B depended on job A. Because job A never completed, job B will never start. So it's important to be aware of these things and to check on SQ to make sure that you're checking out the reason, right? Because if you're just waiting around, if you're like, man, my job is just never starting, this queue must be crazy. We'll check on that. Use SQ to check on the reason, because there might be something like this that's actually causing it to never start. And then for the last category, it says job scheduled and starts but fails right away. So this is much more likely with batch jobs than with interactive jobs. So there's a lot of different things that could cause this. It might be due to Slurm. It might be due to the way that the program is configured. It might be a million other things. This is where job logs play a big role. Remember, logs are the files that contain the output. So these contain the output and error messages that would normally display it in a terminal. For batch jobs, now they're just stored in a file. Read them to find out what might be going wrong. And once again, here are the directives that you need in order to produce these output files. So continuing with Slurm config errors, another type of error that would maybe fall under the category of unexpected behavior rather than something that causes your program to terminate would be unexpected allocation of resources. And this again is related to the managing and optimizing jobs presentation. So if this is something that you feel like you're having some issues with, I definitely recommend checking out that presentation because it'll go into a lot more detail on this. But just to give an overview here, these can happen when the request appears to be valid, but something about it causes the scheduler to allocate different resources than you intended. So an example could be using the total memory flag. Since the amount of memory per CPU is fixed on our system, Slurm will allocate the minimum number of CPUs required to satisfy the total memory request. So if I put in a very high value of total memory and I only wanted one CPU, then I might have a higher amount of CPUs on my job than I expected. So for example, on Puma, this flag here that says mem equals 50 gigabytes, this will request a minimum of 10 CPUs regardless of how many you specified. So if I only specified 5, I might. So the problem here isn't that the job is going to fail. The problem is just that it's behaving differently than you expected. And especially if you are considering how much of your CPU time allocation you're using 10 CPUs rather than 5 is a factor of 2 increase. So if this is a pretty long job or if you're running a lot of them, then this can add up pretty quickly. So it's important to be aware of these types of things. So I included a link to our documentation there on the relationship between CPU and memory. Check that out if this feels relevant to you. And then we also have that whole running jobs section of our documentation that deals with things like this. So how do we avoid Slurm configuration errors? So be detail-oriented when constructing your batch scripts. So don't make assumptions about how any feature will work. Make sure to actually double check with our documentation or with the Slurm documentation about how those features work rather than just guessing. It is, sometimes they are self-explanatory. Sometimes they work a little bit differently than you might expect. Don't copy batch scripts from other people without figuring out what they're doing. Don't use batch scripts from Puma on Ocelote without changing the necessary features. All sorts of stuff like this. It's just important to be attentive and detail-oriented when you are working with your batch scripts. Again, read our documentation. There's the link. And there's also a link there for contacting HPC Consult if you have any questions. And then, of course, read the Slurm documentation. If you're not sure how a particular Slurm function or feature works, their documentation will probably tell you how it works. I have definitely encountered some situations with niche items where the documentation is not particularly helpful. But on the user end, I don't think this will be too much of a problem. There's their documentation website. So let's talk about environment errors. An environment refers to the set of environment variables that determine the paths and point to various libraries and packages on the system. So the command env, if you're on the terminal, will display all of these variables for you. The term environment can also refer to a user-designated set of packages for a particular programming language. And package managers can be used to install these. So for example, with Python, I can have my bash environment, that might be one thing that's going to be displayed with the env command, and then I might also have my Python environment. And together they form my total environment, but they refer to sort of different things. So there are a few different package managers for Python. You might be familiar with pip or Conda. Mamba is a new one that we've been trying to use. So if you are a Conda user, we definitely recommend checking out Mamba because it's going to be a little bit faster and the functionality is pretty much identical. R has this dot in R environ file that you can use to specify a folder that contains all of the packages that you want, and then CRAN, CRAN, I don't know how to pronounce it. That's the online repository of R packages. And then, of course, there are other ones for R, bio, conductor, things like that. So there's a lot of different ones. And other languages and softwares have their own package managers as well. The point here is just they exist and that they can be used to install packages and errors related to your environment can occur at different stages. So if you want to install a package, it is possible for an error to occur there during the installation of the package. Depending on the type of package manager you're using, sometimes, for example, R packages do get compiled when they're installed. So compile time errors for things like that can occur during the installation process as well. So those can be error prone. We will talk about how to avoid those errors. The second one here is runtime error. That's when the program is actually executing. And this could be related to the value of different environment variables or the location of packages, or maybe usually version conflicts will occur on the installation side, but every once in a while it is possible for them to pop up during runtime. Maybe you wrote your code expecting one version of a package, and then you ran it in an environment that had a different version, for example. Okay, so installation, what's happening during installation? Your program is looking for the packages it needs to run. These are referred to as dependencies. There can be many layers to dependencies. So, maybe the package that I'm trying to install, package A, it's not just that package. Maybe that package was built or developed with other packages that were pre-written that it needed in order to execute the things that it needs. So you can end up with these layers of dependencies. Sometimes they are implicit, meaning they're not explicitly requested. I say install package A, and then my package manager goes and installs package A through Z, right? There might be as many as dozens of packages that need to be installed as the backend for the one that you actually want. So this can be very confusing sometimes because an error might be related to a package that you've never heard of and don't remember requesting because of these implicit dependencies. Usually your package manager will tell you everything that it's trying to install, but of course, if it's not the thing that you actually wanted, it might be difficult to remember what those were. So because of these implicit dependencies, it can be quite complicated to create an environment that is self-consistent and not prone to errors. So users who are familiar with Linux might know that apt-get command, which I believe now is just apt. So just continuing to talk about package managers here. So this is a command for a package manager for the Ubuntu operating system. It cannot be used on the HPC for the following reasons. First of all is that the HPC does not use the Ubuntu operating system. So this command only works for Ubuntu and Ubuntu-derived operating systems. That is not the case for HPC. The second one is that the package manager requires administrator privileges. Users do not have administrator privileges. So both are pretty concrete, unmovable reasons why it is not possible to use apt-get on our HPC. And for the second reason there, the fact that users don't have administrator privileges, package managers like Yum or Pacman cannot be used as well. So Yum would be the package manager that we would actually use, but still that's only reserved for sysadmins, not for users or even for us consultants. So even if a package is available via package manager, it cannot be installed this way on the HPC. Users must download and compile or install it from source or find another method to install. Or if it's a system package, you can message us and we can see if it's possible to install that on our end. So Linux package managers are pretty much always a no-go on the HPC. So don't, if you're looking at your software and it says use apt-get, you should immediately know I can't do that. I have to find another way of doing this. And if you're struggling to find the right way of doing it, feel free to message us. We'd be happy to assist. So, yep, link right there, contact HPC Consult if you're unsure how to install the software you need. So some best practices for environments. I know we're kind of running up at time here, but let's see if we can get through these. So first of all, check out our workshop on environments for more detail, but here are a few quick ones that hopefully can help you prevent errors. So first would be to create new environments based on function. So one of the best things you can do is to avoid installing all of your packages in a general purpose default environment. This might be the easiest thing to do. I don't want to have a million different environments. But if I install all of my packages for a variety of different purposes in the same environment, it's the more complex the environment gets, the more likely it is for it to run into errors. So this can cause bloat, slowdowns, and conflicts. Definitely best to try to create a different one for each function. So I do have a general purpose environment, but I specifically avoid installing any special purpose packages in this environment. If I know that I need a special purpose package, which, what determines whether a package is special purpose or not, I guess it just maybe in the context of projects that you might be working on, right? So I try to take those specialized packages into particular environments and then have a general purpose environment that just has very basic packages. So for Python, it would be something like my general environment would have matplotlib and numpy and pandas and things like that. Whereas if I were doing a special purpose environment, say, for example, MPI for Pi, I keep that one in a separate environment. And I keep all of my astronomy packages in a special purpose environment as well. So that's just sort of the approach that I take that I recommend. So project environments are designed to accommodate those special purpose packages. So that way, if it needs any weird particular version of some dependency, that it can do that without conflicting with the packages that I have in the general purpose environment. So hopefully this makes sense. Create new environments based on function, and what designates whether something is special purpose or not, that's really up to you. But hopefully there's, hopefully this gives you an idea of how to go about this. So another best practice here is to use one package manager to install software to a given environment. So for some softwares like Python, they do have multiple package managers available. But if you are creating a package manager with if you're creating an environment with one package manager, then stick to that. Don't try to switch it up. Even if there's another piece of software, if I create an environment with pip and then I find out, oh, well, I need this other package that's only available via Conda, well, then I should go create a new environment with Conda for that package. I shouldn't try to install that package in my pre-existing pip environment. So don't cross the streams. Don't manage, package manager A sticks to environments created with that one. Package manager B sticks to environments created with that one. And you shouldn't try to use package manager B to install something in one that was created with package manager A. Hopefully this makes sense. So document your environments. This doesn't have to necessarily be done by hand, but if you are working on your environment and you get everything installed and working and everything is pristine in the way that you wanted it to be, sometimes the package managers, almost always the package managers, have ways of just printing out the environment. So it'll print out the package, it'll print out the version of that package, and then just print them out, save it to a file, and say, this is what my environment looked like on, today's date, right? And that way, if you install something later on that breaks your environment, you can go back to that list and reference it in order to recreate your environment the way that it was before. Try to stay updated with components and packages when possible. Sometimes specialized packages are built on older versions of things, but and that might require you to use some older versions, but do try to use the newest possible version of things that you can get. Don't, if you've had an environment sitting around for 15 years, it's probably time to update that, right? So generally, just try to make sure everything is as up to date as possible. Sometimes it is acceptable to go back by a few minor version numbers. So minor version numbers, if you have major version number A, intermediate version number B, minor version C, so 4.1.3, maybe fine to go back to 4.1.0, maybe even fine to go back to 4.0 if a necessary component is incompatible with the newest versions. But again, try not to go back too far. If you are a Conda user, we highly recommend you at least give Mamba a try, because this is a new package manager that is much faster than Conda, has all of the same functionality, and is generally better for HPC systems than Conda. So if you have the opportunity and you're a Conda user, try to replicate your environment with Mamba and see if it works, see if you like it. The functionality should be more or less the same, and we do have some pages in our documentation related to the switch. Okay, so we got a few left to go. Not too many though. Out of memory errors, pretty self-explanatory. Common abbreviation is OOM, so keep an eye out for that. Oftentimes, if you do get an error message related to this, it won't explicitly say out of memory, it will just abbreviate it to OOM, so just be aware. This means that the amount of RAM or memory available to your job was insufficient. It tried to load some data and ran out of space. This does not refer to disk space, but program memory. There's a link there if you are not sure as to the difference between the two. The fix is pretty simple. Just resubmit the job with more memory. This is typically done by increasing the number of CPUs allocated to the job. If it's not always possible, it is not always possible to predict the exact amount of memory your job will need. There's not some equation that we can write down that will tell you, oh, my job needs 7.3 gigabytes of memory, right? But if you're loading a data set that exists on the disk, then you can use that as a good lower bound for the amount of memory that you might need. And of course, it's good to try to get that as close as possible. Generally, it'll make more sense to overestimate, because if you underestimate, then you'll get one of these errors. So try to overestimate, but not by too much. That's the general process here. Compile time errors. So if you are compiling your own code, or if you're using a package manager that compiles on the back end, these can be related to, but can also be distinct from environment errors. So compile time errors often occur when a user is trying to directly compile software from source. Generally speaking, this is an acceptable and recommended practice. We do ask that if you are compiling, that you do it on a compute node rather than on a login node. But sometimes the compiling can be tricky depending on the software. Sometimes it's a breeze, sometimes it's not. So as I mentioned, this also occurs for package managers that compile packages on the back end. So I guess I forgot to do the animation for this slide, but we'll just read through them. So as always, first step, read the documentation. So especially for packages that need to be compiled, usually they'll have some level of instruction in their GitHub or on their website, wherever it might be, that tells you about the necessary libraries that it needs. So you can go read that and find them on the HPC. So that means for step 2, loading or unloading the required modules. So unloading would be necessary if the particular module that you need is in conflict with one that might already be loaded. For example, the Intel MPI module is not compatible with the OpenMPI module. So I would need to get rid of the first one in order to install the second one, right? So finding system libraries would also be part of identifying the libraries needed for compiling. So sometimes software might be in the operating system rather than in the module system. So you can use this command ldconfig to find them. So ldconfig-p, that prints system libraries, and then you can use grep to filter out the ones that match. So in this case, I was looking for something related to Fortran, and I did ldconfig-p, pipe that into grep for Fort, just because that's a common abbreviation in Fortran codes. So here I found libg fortran, and I found the path that it goes to. So if my compiler needed that, I would need to include that path, either in the makefile or as a compiler flag. So using the right combination of -i and -l to specify includes and libraries, depending on how complex the software is, it can take some time to figure out the right combination that will make it compile correctly. And again, with this one, definitely patience and growth mindset is necessary because it can be a little bit frustrating at times. So continuing on here, recap of the presentation. We're basically done now. So as always, read the documentation. That means our documentation, and that means the documentation for whatever software that you're using. Next one would be to be aware of and use best practices. So we talked about those pretty much at the beginning of the presentation. And then adopt a good mindset for this. So that means be systematic, be open-minded, be growth-oriented when bug hunting. If you do want to use AI tools, make sure to use them carefully and to verify things independently. And lastly, as we spent the last half of the presentation talking about the common bugs and how to avoid them. So hopefully that was instructive and helpful for you. Here's our slide on our consulting services. So I'll stay on for a minute or two if anybody has any questions. Otherwise, I'll see you next time. Yeah, thank you.